This will be a quick overview of for loops and nested for loops. If you're having issues with the lab, towards the end of this video may help you out. So anyways, you'll begin to recognize the power of code when you learn how to use loops. Computers are very good at executing repetitive tasks very quickly. And you can really start to appreciate loops once you write a decent program that uses loops to accomplish a task. And then if you take a step back and imagine what the code would look like without loops, you'd see that it would get pretty out of control. So we've all seen for loops by now, but just a quick review. This first section is typically an integer declaration of I and an assignment, and the middle section is some sort of Boolean condition using I, and the next iteration of the loop will only execute if this condition is true. If it's false, we'll break through the loop and continue on with the rest of our program. This third section is where we update I, which is important because if we forget to update I will persist as 0 and I less than 4 will be true forever. So in this case we don't want a loop that runs forever because we're trying to count from 0 to 3. And one thing I'd like to point out about this condition here is if, for example, I were to assign a value to I, that would make this condition false, and then have something else in the loop. This statement will still run once we assign 5 to I, because this condition is only evaluated before each iteration. So when I is 0, it will enter the loop, print this statement, will assign 5 to I, but the loop doesn't magically know that that condition is false because it won't check it again until this statement runs, and then we come back up to the loop. So just keep that in mind. Also, we could have a different kind of variable here, such as a Boolean, and that would be perfectly fine. But usually in a situation like that, people would use some sort of while loop. And as I mentioned, all the loops are equivalent. A for loop can do anything a while loop can do, and vice versa. And same with a do while loop. It's just that there's situations that make more sense with one versus the other. So for loops are typically used when you know a starting point and some sort of ending point beforehand. While loops are typically used when you're not really sure how many times you're going to be running your loop. So anyways, let's see this print. So yeah, you can see we entered main, our loop ran 4 times, and then we continued on in main and exited. So another thing to think about when you're writing a loop is whether or not you need the information that lives in the world of the loop needs to persist outside of the world and in the world of main. So what I mean by that is if we only wanted to count, then it's fine if we just print I and we don't keep track of anything. But for example, if we wanted to do that, but we also wanted to calculate the sum of every I value, we would need to declare a variable outside of the for loop scope. We need to do that because if we try to keep track of something like sum and declare a variable inside of the loop, well, if you'll remember the scoping rules, this block of code belongs to the for loop and will be re-executed with every iteration. So everything in the world of the loop will be recreated, reran, and then destroyed at the end. And then on the next iteration, we'll make another instance of S and assign it 0 and run the print statement, and then all that's gone. So we'd lose information that we want to persist throughout every iteration of the loop. So to finish the sum example, all we would do is say sum is equal to sum plus I, and then go ahead and print that out at the end. Yeah. So in regards to the lab, we used a nested loop. So we had another for loop inside of our initial I for loop to represent a two-dimensional grid. And whoops, I need to use J. So let me get rid of this. We don't really need it anymore. Yeah, so we can calculate how many times statements will run in nested for loops by simply multiplying the number of times J will run with the number of times that I will run. So a statement here will run 4 times, but a statement inside of J's loop will run 16 times. And if we had another loop inside of J, the statements inside of that loop would run 64 times, and so on. So in the lab, we wanted to use the nested loops to represent a two-dimensional game grid. The grid would have, in this case, a total of 16 squares. 1 square for each unique combination of I and J. So to demonstrate that, let me interpret I and J as a pair of XY coordinates, or row and column, or however you want to think about them. So I'll go ahead and make it look semi-nice. So we'll print I, and then a comma, and then J, and then closing bracket, and a couple of spaces. So the way I have it now, it won't actually print very neatly because, well, I'll just show you. So we still have all of our unique XY value pairs, but it's printing on a one-dimensional line. So if we interpret the J loop as printing out every square in an entire row, then once we're done printing a row, we want to print a new line. So let's add a print statement outside of the J loop. So yeah, that'll print a new line, but I'll print 2 new lines to make it look nicer. So now if we run it, it'll look more like our 2D grid. So you can see we have 4 rows and 4 columns, each of which having a unique row-column pair. So in the lab, we had these loops inside of another loop because we can kind of break this chunk of code down to the logic to draw the board. But with the game we had, every time we drew a board, we would get user input from the console and get a new location for our character. And once we did that, we would update the XY values and then draw the board again with our player at the updated position. So I won't do that here, but I will demonstrate the idea of wanting to keep track of information that persists outside of our logic to draw the board. So let's go ahead and declare a player X variable and a player Y variable. So now we can assign a unique IJ pair that will represent our player's position in our little world. And just a side note, if our world was a three-dimensional one, we would need an additional for loop inside of J to represent both X, Y, and then the additional Z space. So rather than printing out I and J, let's go ahead and get a yes or no answer to whether or not our player is at the current I value and current J value. So I'll make a boolean and call it player location, or player is at, and we'll make that equal to true only if player X is equal to J, but not only that, because we also need to compare I with the player's Y value. So we'll add the logical AND operator and check if player Y is equal to I. Okay, so now at this point we have variables to keep track of our player, we have our logic to draw the board, and now we have a yes or no answer as to whether or not the player's at the current square that we're drawing. So in the lab, that meant the difference between printing out an X versus an underscore for empty space. But here I'll just go ahead and print out the boolean. And actually, I'll rename that. So now we know if player is here, and I'll go ahead and add some blank space just to make it look nice. So now when we go to run it, we have our yes/no answers to whether or not the player is there. So you can see true moving around the board when I update the values and rerun the program. So yeah. And now you see why we had all of this inside an additional while loop, because it would be a pretty boring game if we had to stop playing and restart it every time we wanted to move our player. So I'll go ahead and finish the video by putting the player here and running through our loops with the debugger. So the X value here is 3, and we're at row 0. So that would mean Y of 0. So I'll set a breakpoint and run debug mode. And now we can watch the game board being drawn as we loop. So no, no, and there he is. So yeah, the loop will find him eventually, regardless of where he's at, as long as he's within range of our loop values. And actually there's one more thing I want to demonstrate, is at a higher level it's up to you as a programmer as to how you want to interpret the information that you're creating and manipulating. So what I mean by that is, if we comment out this line here and rerun that, well, now it seems like we don't have a two-dimensional space, we have a one-dimensional space. But really the information we're keeping track of is still the same. So if you remember from the beginning of the class, I mentioned that code is actually pretty complicated. So if you can structure your code into logical pieces, it makes it easier for humans to understand what's going on, which is assigning decent names to what you're trying to represent and writing code in modular chunks, like all of that. I decided was my logic to draw the board, and what have you. Which, at an even higher level, is kind of the idea of an object-oriented programming language, which Java is. It's a nice way to abstract complicated details into logical pieces that we can easily understand. But we'll learn more about that when we get to classes.